Please welcome Wojtek.
Hi, thank you very much. Well, let's start this way. I always wanted to be a computer scientist, IT guy, whatever, to deal with computers and to solve hard technical problems. So that's what I do. I've worked for 15 years on a technical university until I had enough. So for last 4 years, I work at FLYR and still solve hard technical problems. I also co-organize Rzeszow Ruby Users Group, so please don't throw hard things my way. Please be tolerant. Okay, guys, what about this? I would like to tell you a story which begins in the ancient times. It was a long, long time ago when Middle Earth was still a young thing, actually around 4 years, okay, ago. What's the story? When I joined FLYR, more or less by then, there were microservices in FLYR and they communicated via HTTP. That's how it was solved by then. And then was also a moment when FLYR received a new requirements like e-commerce related thing. It's not very important like what the use case was, but I will show you more or less how it looked. I was a new joiner and I got a new task. So it was like, you are good enough to do this for us, but you know, I wasn't in a position to question all the decisions that were already taken. So if you, like when I show you that, take it into consideration also. Some of your questions, why this or that, will be answered because, you know, I couldn't change it, okay? What was the use case? The use case was that, imagine we have a UI backend. This UI backend will be receiving some requests from frontend. It will be, it will be a kind of search request, let's say, okay? And to fulfill this request, to respond, we knew that this backend will have to contact a special service, but this service will also not have all the data required. This service will have to query a lot of different other services. Some of them will be external, like external integrations of our system with external providers. Some of them will be internal, okay? So if you think about it, what's the user experience when you send a HTTP request and to get a response, your backend needs to send a bunch of other HTTP requests, maybe outside, to get responses, await for them, then combine them into an answer and give it to the user, like, okay, let's go for a coffee or something like that. So the goal was to provide better user experience. You know, we can cheat physics. Physics is physics. The time is time, it adds up, and we can't do anything about it. But what we could do, we knew that some of the answers we will receive pretty quickly, especially from the services we own. That's something we can manage, okay? So this internal service you see is something that can deliver a response pretty quickly, but maybe it can be further improved when we get more results maybe from external services later. So the idea was that whenever we get something that is already useful for a user, we want to send a kind of partial response for the original request to show something useful to the user. And then when we get another response a little bit later, we will send another partial response with a better result for the user. And it's up to the user to wait a little bit longer and maybe get better results, or decide that it's good enough for him or her and go with whatever we've already shown, okay? So the schema from technical point of view was like we send a single request and this may result in a lot of partial responses, arbitrary number of partial responses to this original request. Of course, there's a lot of ways that we can solve it in technical, from technical point of view. We can solve it using the HTTP still, okay? But it was like the last straw that company saw to convince them that we probably need something more than the HTTP-based communication in our microservices. The other was related to performance. And here's my fault. I never took notes with numbers then. What number of requests could I expect? These were not very good numbers because the estimation looked like, you know, Wojtek, there is this number of bought items during the day for this customer. So imagine how many such requests would a customer send to do a one purchase. I mean, you imagine it. We don't know. You try. And then think how many actual technical requests will be required for this search request. Multiply all these things, and you will know how many like messages or something you will have there. So it's not a very good estimation. But that's also an important lesson because it appears to be sufficient to take decisions I will show you later. Okay, okay, let's go for the further things. So this was the moment when a company decided we want the message queue-driven communication due to these requirements, due to performance requirements, due to the fact that we know that we will develop this thing in the future and we expect that still we won't be able to handle it over HTTP. Let's do it, Wojtek, do it, okay? Do it for us. Okay, let's go to MQ. We know we want to do it. We want to switch. The decision is taken, well, but we have these microservices communicating over HTTP. It's like something up and running, okay? We have developers that worked on that and that have specific mindset, which is specific to the HTTP communication, where it's synchronous. When you send a request, you wait, you get a response. There is no problem with that something happened during that request and things like that, okay? So there are habits that may be hard to change. Also, we lack experience with MQ-driven communication, and of course, as always, no? You must do it well the first time. Of course, we also know what everyone can Google, that when you do MQ, you have all these nice things in your CV, in company, leaflets and things like that. That's just perfect. But when you think a little bit longer, you realize that you also have new opportunities to like make all these new mistakes you never experience with HTTP-driven communication, and it's like concurrency through race conditions. These are inherent to asynchronicity, but there are more. For example, if you can select incorrect broker. Which broker should we select if you don't have experience with any of them, okay? If we select a correct broker, then which driver should we choose? Did you look at the Kafka drivers for Python? You are a newbie and check how many of them there are and why should I choose this over that, okay? It's not an obvious choice. So we may make a mistake here. If you check how to use a driver like this, then it's again not obvious thing because even the driver is asynchronous, so you may end up using it incorrectly, and you have a lot of microservices, a lot of teams using these microservices, so if they all start using it incorrectly, we may end up with a lot of mess. And then, even if we choose correct broker, then still we may use the broker incorrectly. So another idea, and this is the most scary part, at least for me always. You know, the thing you not even know that you should be afraid of, okay? So a lot for the start. So we decided to contain all these risks in one place. I mean, a kind of library that would encapsulate all these risks whenever it's possible, or as much of these risks as possible. We called it asynchronous because, well, no better idea for a name, and you know you have to put something in GitHub when you start a library. So what was the idea? We create a possibly small library, so not a framework. We don't solve all the problems, but we want to solve this single communication problem in this library. We wanted to make it as easy to adapt for our developers as possible. We had these microservices based on HTTP, so we wanted this library, if possible, to resemble at some point the same thing. But the communication below should be message broker driven. So what we got the kind of advantages, like, you know, for all bugs, one place to fix. For all decisions like brokers, drivers, and so on, one place to change it, okay? For all usage patterns for drivers, also one place when you can improve these things. For developers, you know, it's always better when the complexity is hidden because it's much easier to adapt to a new thing. So the entry barrier is lower. So what were the decisions that we had to take in a way at the start? We chose Kafka as a broker, and these are the two most important reasons. First is that Wojtek, it must be persistent, no way. There is no way you do it the other way because we don't agree to lose any messages, okay? And okay, you could argue that if you take RabbitMQ and there is a cluster and things like that, no, it's in memory, you know, no way. At this stage, no way. So if no way, then no way, because if you take RabbitMQ and turn on persistency, then the performance is so poor that it was way below our requirements. And that is the point where the rough estimation I mentioned, how many messages might I have, it was really poor, but it was pretty sufficient to decide that no way, whatever it is, it won't fit into Rabbit with persistence, so we end up with Kafka, okay? That's an important lesson because sometimes we go to our product owners and ask them questions, how many, how much, and they don't know that for us, the very rough estimation may be pretty sufficient. It may actually allow us to take a proper decision. For Kafka driver, we choose Confluent Kafka for two reasons. First, performance. It's meant for performance. It's designed for performance. Second, you know, it's Confluent, so it should well work with Confluent Kafka. There should be no bugs and things like that. Oh yeah, sure. We learned the hard way that it's not like that, but well. Okay, so the assumption for the library was provide just IPC, no, nothing more, so no framework. The second, make it testable. So if like when you have a HTTP microservice, you can do different things with that. You can automatically test it, sending a request from your PyTest or whatever you prefer and checking the response. You can manually test it using SURE or something else. So we would like to allow developers to do the same thing when they use our communication method to make their life as easy as it is possible. And last thing, we had these microservices based on Flask, so we would like this library to resemble Flask from the API point of view, so it's easier for developers to understand how they deliver the communication points or endpoints or however we call it, okay? Talking and talking and talking. Who showed this movie? Who saw this movie? Have you? What kind of movie is this? No. But yeah, that's the face, but not the movie. That's the movie. Jerry Maguire, yeah. That's right. That's right. Not much code today, but just a little bit, so you see how we solve the like the interface thing. You create an object, giving it a name. This name in async calls is a name of the service you are implementing. It will be part of the address for any message sent. Then if you want to create the endpoint, so something that reacts to messages and responds to messages, you do it similarly as in Flask or Fast API currently. So you create a function and provide a decorator defining that it's an endpoint for, and it's again another part of the address in the parameter. If you see this loop inside, it mocks sending 5 responses for the single request with some period of time in between. Okay, so you have a request and 5 responses sent in this example. This response object is created from request object, and there is a correlation ID between these two. So when you send the request and you get the response, then you have a correlation ID inside, and you can check for the response for which of your requests it is. It should be matched. Okay, this is like a server side of the idea. The client side looks similar, well, you create a new message from async calls, giving it a destination address. It's a service ID, service name, and the endpoint inside, and the payload. And then you just send it, okay? But it's all, of course, non-blocking. So when you send it, it's just, it goes to the queue. So to be able to react to any response that is received, you again have to create a callback for responses, and this callback will be called whenever a response is received. Then you get a response object, and you can deal with it. Okay, so that's client and server, and all of it is non-blocking. So in the end, you have to provide call a listen method, and that's where the loop happens, and all these callbacks are actually called whenever a message is received. Okay, and the thing is that, of course, below that is the Kafka, and it just delivers these messages, but it's not something you have to deal with when you use the library. So what we have a server which looks pretty much like what we had for HTTP. We have a client which is non-blocking and event-driven, so it's way different than what we have in case of HTTP, but it's pretty similar to the server, so it should be pretty well understood by developers, although it's not so easy. We have fulfilled the requirement that you have one request and then a number of responses for this. And when you implement if you have a service that should receive some requests and then send some responses, react to the, but before the response is sent, it should send another request somewhere else. You can do it inside one single process, because one single process can act on requests and responses in an asynchronous way. And now, how could we test it? Okay, the library had a testing mode meant for automatic testing. So the first scenario which was supported by this testing mode was very simple. In your automatic tests, you could create a test client or mock client that you could use to send, mock sending messages to your service, the one that you were testing. Okay. Then the code of your callbacks was invoked, and then the response was returned to the test client or mocked client. And in the end, you could take this client and assert if the client received the responses you expected. So it was pretty simple. But it was not the only scenario that we found required, because sometimes when you test these kind of solutions, you have a case where the tested service, the one in the middle, Of course, it should respond to the request it gets, but in the meantime, it should notify something else. And we want in our test to also assert that the notifications were sent correctly. So the other thing you could do in your test was to create another mock service, give it a name or address or something. If you knew that your service should send notification to something on notification receivers, you just created a mock of something like this. And then in the end, you not only asserted that your client received expected responses, but also you could take the object of this notification server and check that this notification server got the correct notifications. And last and most complicated case is that the third service is actually not just a notification receiver, but it also is expected to deliver you some data, and only then your service is able to respond correctly. And so in this case, the third service, the mocked one, could have a generator that provided that whenever a message reached the service, it responded with some predefined value. So you had deterministic responses coming back to your tested service, and you could then check if the service responded correctly. So the testing tools for automatic testing we had out of the box in the library. All the calls in testing mode were made on stack. It wasn't Kafka below that. So a lot of the library was mocked for this purpose. So this was completely deterministic. If you send the messages in specific order, you received, if you sent, for example, 5 responses in specific order in your test, then they were received in specific order. If you wanted to test some reordering in messages, then you created 2 tests with different order of requests, responses, or something, and you always had deterministic tests that proved that things work correctly in both cases. Okay, to run these tests, you didn't need message brokers, so it was way faster in that case, aside from that it was deterministic. And when you tried to test it, you didn't have to think how to mock this MQ broker below, so I can catch the messages that my service should be sending and respond, fake it somehow, and things like that. It was already done, so writing these automatic tests was also pretty simple. We also added more features to that. I won't describe them all, but something like hooks before and after the request was served, or context manager that spanned the request processing, a Kubernetes health check, and things like that. And for manual testing, we had a client that looked something like Siurl, that allowed you to manually send a request with specific payload to a given service. Okay, of course, when you hide the complexity behind some abstraction, you also hide a lot of opportunities. So we also did this, and if anyone asks, could we use Kafka streams over this your library, then of course you could not. Okay, we hid a lot of opportunities with that, but it's not something we needed. Okay, we just used the Kafka for this specific purpose we wanted. So what did we achieve? We still ended up having things like concurrency issues and race conditions, because, well, it's asynchronous communication, so there is no run away from that, no way to help it. You need to learn how to deal with these things in your code. But for the incorrect broker choice, well, if we had to switch from Kafka to, for example, Rabbit in this case, we would have to rewrite probably 2/3 of this library to make it work, but we wouldn't have to touch any of the microservices using it. Okay, so it would be a lot of work, but, well, feasible, and we wouldn't touch the company actually at all. For the incorrect driver, if we had to switch from Confluent Kafka driver to something else, it's like 1/3 of the library probably to be rewritten, but still not so much, and still we don't have to explain the other teams that you have to now do this or that and put tasks on their boards. For the other things like incorrectly used driver or broker, we had these issues, and today no one knows that we had them, okay? We didn't explain, we fixed the things, no one noticed. We knew, so we fixed, but no one noticed. For the driver, we had an issue with incorrectly working Confluent Kafka driver. It was a very strange issue. I debugged it for a long time until one of my colleagues said, hey, there is a little bit newer version, like patch version, a little bit higher. Try to upgrade it, and it fixed the issue. Okay, so that old version didn't behave like Kafka at all, for some reason. So when we tried to switch from HTTP to Kafka, tried to switch a service, because we did it. We had a service which was exposing HTTP API and this Kafka-based API at the same time, both of them. It was really fun thing to do because you just added a few functions that were calling the same business logic behind, but were decorated to use Kafka, and that was more or less everything you had to do. So yeah, it worked. For the client, it was way more complicated because there were these callbacks and asynchronicity, but it was the idea to have it this way. It also supported one-way communication because you could have a case where someone is sending requests and not expecting responses. So when you wanted to do just a one-way communication for any reason, notifications or something like that, it was pretty feasible, and we did this. Of course, if you consider more complex cases, this requires more attention because, for example, you can easily end up with callback hell on the client side, but it was not something we wanted to solve in one place. Maybe build something on top of that later. And the services were easily testable, so there was no problem here. So we end up with a standard Projectwide layer for an asynchronous communication. Also, these things related, to Kubernetes health check and things like that, they were very useful, and we spent quite some time to do it well. So doing it for each service separately would be a hard thing. But this is first part of the story. Then, when we had this and it worked, we started to implement it in different places in our system where we realized we need it. Not everywhere, just switch all the communication this way, but where we needed it. And then we started learning a lot about how the asynchronous communication works and what are the results of that, what should be done and what definitely shouldn't be. And that's something I would like to share with you today. So the war stories. Let's consider a use case like this. Of course, it's all simplified, but we got two message streams coming from our external integration. The stream below provided changes. Let's think that it's a new booking for a flight. So someone bought a ticket or 6 tickets for a specific flight. That's a notification you can get on the stream on the left below. And these changes should be integrated or summarized by the service one. So the service one should calculate, if we got 6 new bookings, then there is 96 bookings for this flight. And this information should be sent to service 2 over another asynchronous interface. So this flight, 96 bookings. And then there was an HTTP API exposed by service 2, so anyone who wanted to know how many bookings for a specific flight there were could ask of the service 2 over HTTP. So that was the idea. Okay. We also knew that if we go only with these changes in bookings for long enough, we will have the synchronization between the source system and our system, because there is always a possibility that something is lost, that the source system, of course, we won't lose any message. Of course, we will process everything correctly, but it will always be their fault. They didn't send us a message or something, so that's why there is a difference. But okay, but we wanted to avoid these situations, hence the upper stream from our integration, and this stream should send rarely, not so frequently, because the below one was like real time, but this one, once at some time, should send us a summary with information. For this flight, we currently have 70 bookings. For that flight, we have 20. So in that case, the service one should update its current state for the flight and then start updating it again from the real-time feed. Okay, so the happy path was like this. We get a message, we update the current state of sold seats in a flight, and then send an update to the service too. That's what we think. Of course, we had the duplication implemented, we had message versioning correctly done as it should be. Whenever there was an exception which was not correctly caught in our code, then we correctly handle it in a way that Kafka will not commit the message in the message blocker, okay? So if we got a message, this caused an exception, then the message was not committed, so Kafka knew that should redeliver this message later. Okay, so what could happen in this scenario? First thing, we receive a message, we try to commit it to our database, and the commit fails. Before we even saved it to our Postgres, there's a failure. How do you think? What will happen in this scenario? Which commit, Kafka or Postgres? So no, there was no Postgres commit yet. Yeah, you said resend the message. Yes, Kafka will resend the message because the message was not committed to Kafka, okay? So this message will be redelivered. Because it happened before anything was committed in Postgres, message will be redelivered, we will process it again. Hopefully this time we are happy. For example, let's assume that previously, I don't know, Postgres was not available for a split of second and it failed. So this time we may process it correctly. And then we are supposed to send a notification to the next service. So we process the message. We committed the message in our Postgres. We are sending the notification to the other service, and now we have a failure because Kafka was not available for a split second. So what now? Three? Yeah. It should be what? I was going to say it. I was supposed to do it, yes. Yes, so the idea is that the message shouldn't be marked as, you mean the original message, right? The original message, that one coming into our service one, shouldn't be marked as done before the next message is successfully sent to Kafka, okay? And I was going to give you this as a final solution we found. Thank you. We were thinking quite a while to find this solution. Well, yeah, what we actually did, was the commit of the original message we received was done only after Postgres commit succeeded and Kafka send succeeded. Okay? So, but it's not everything we had to do. But because now imagine that the failure happened, the original message was not committed to Kafka, but we already had a commit to Postgres. Okay? So we received the original message again, and our code said, man, it's duplicate. So what do you do with duplicates? Ignore it, right? So if we did only this, then we would end up with what? Correct state of service 1, because the message was processed, but incorrect state of service 2, because the message there was never sent. What should we do in that case to fix this issue? That's another solution, yes. It's another solution, but until we go there, let's finish this one, okay? And solution for this one was that whenever we get a duplicate of a message, we of course don't process it to our Postgres because it was obviously already processed. But we still take current state for the related flight from our Postgres and send the notification for this flight to the service 2. Whatever, if we get some duplicates on the first flow, we will end up with another duplicate on the second flow, but it's not a big issue. There won't be so many duplicates. But this way, like simple solution that allowed us to fix this issue. And now, coming back to the other solution, and probably the one that you would like to choose when you were in our case, because it's more general, and probably it will cause less errors. It's called outbox pattern. I believe Martin Fowler describes it. Who heard about outbox pattern? Not so many. If you want to send messages in this scenario, that you upgrade your relational database and send notification, before you start designing it, read about outbox pattern. It's a pretty simple solution. Instead of sending the message to the queue, you have a specific another table in your Postgres database. Let's call the table outbox. So when you commit changes to your Postgres, you prepare a message that you would like to send. Instead of sending it, you insert this message to the outbox table in your Postgres in the same transaction in which you commit the changes to Postgres. Then you commit. Either the commit succeeds and you have the changes and message committed to outbox, or the commit fails and you have everything rolled back. There is no message, there is no changes, there is no problem. Okay? Now you need a process that will be taking messages from the outbox and sending them to whatever broker you use. It can be a salary recurring task. It can be triggered after your processing, after commit. Anyway, you should have another process because after a crash and restart, something should pick up the messages from outbox, okay? So there is a few things that you need to think about, but then in any case, you have a secure way to send messages, send notifications about changes in your relational database. The downside is that you may end up with duplicates of these notifications. But if you have a message-driven communication, you must deal with duplicates, and there's no way around it, okay? So yeah, that's something to remember. And the third thing is that the failure may happen here when we are trying to save the new value to the other Postgres from service 2, and what happens in this case? Anyone? Yeah. Same story as with the first one, okay? So that one is pretty easy, okay? Yeah. So that's the first stream only, okay? Now we have the other stream, the one that is sending us snapshots for some time, and we need to deal with it. Of course, happy path is like this. So we have some real-time feed changes sent, and between them there is a snapshot at exactly correct point of time. We receive it, we apply it, and then we have another incoming messages updating the snapshot. Of course, in reality, we will get something like this, that we get a snapshot, we look at this and realize, well, but after this thing, we already processed the 15 other messages updating in correct state, okay? Because the snapshot is older than these messages. What should we do now? We already processed these messages and dump them, remove them. What's the solution here? Yes, we can detect that the message is late, and we detected it, and so what now? How long? Yeah, that's tricky. Yes, yes. Yeah, that's also tricky. Especially that you can't, you know, it looks easy when you have numbers, but we didn't expect the snapshot to contain all like million flights for a whole schedule, okay? It would be a part of the schedule, so you would get snapshot for just a few flights. So it would be tricky to query from Kafka the correct messages that applied to these flights or replay a lot of messages to find the correct ones. So we ended up in creating a kind of inbox where we stored all the incoming messages with timestamps. So whenever we received an old snapshot, we applied this snapshot, overrode this data in our database, and then found all the newer messages in our inbox this time. And the same code we used to apply these messages when we got them from Kafka, the same code applied these messages again on the new state when we received them from our Postgres inbox. Of course, we ended up with the need to keep that inbox and to find a way to purge it at some point and decide when we can purge it and when we shouldn't remove messages because they still can be useful. It's a tricky one too, but you know, it's always a trade-off. And now, one last thing. It's been 4 years, so I hope these crimes can be punished after 4 years, so I can admit it was my stupid idea. The case was like, you know, guys, there is this service, it will expose HTTP API, and you will receive some notifications from this other team, and you will have to get these notifications, update your state, and your thing is to expose HTTP API so the others query the state. But, you know, that team is very busy now. They won't have time to design this together with you, so you have to design this now yourself and implement it, and do it well, because when they will have time to start using your interface, then you'll be very busy, and you won't have time to update it or whatever, so they will have to integrate with it and be able to do any changes that are required there, okay? Well, okay. Pretty frequent case of desynchronization between teams. Why should we synchronize? We have separate teams in the end, okay. So it was my idea, okay, if we give them the CRUD, then they will be able to do anything they want, right? No, well, right. So what's about the CRUD over in case of asynchronous communication? What can we expect? For example, imagine that you have this CRUD, so you have your delete, update things implemented. Of course, you have message versioning because there can be reordering. And you get an update message with version 1. You see the message and you see that you don't have this resource in your database for some reason, okay? In HTTP, you would say, well, that's an error. I don't have this resource. You can't update it, okay? So, PagerDuty, right? But on the other hand, maybe it's something Maybe I shouldn't do anything. Maybe just a warning. Why did I get this message in the first place? Well, why? Maybe it's just a strange message that I got. So someone thinks that I have this resource and I don't have it, so I should definitely report it. If it's PagerDuty or warning or just info log, it's up to me, but I should report it because there's inconsistency in the system, okay? But maybe it was just like below. Someone updated the record, so update message was sent, and then deleted this record. So delete message was sent, but I received them in incorrect order. So I've already processed the delete message. It was fine. I deleted the resource, then I got the update message. So what? I should ignore it because it's an old message. And it's not relevant since the resource was updated. Now imagine that we go with the PagerDuty, it's Monday evening, it's Sunday evening, you get the PagerDuty, and after an hour of debugging, you realize it's the second case and you shouldn't even be looking at this, okay? So what's the solution? The solution is that when someone deletes something over this kind of interface, you can't delete it. You actually should mark this as deleted. You should remember the message version number that deleted this record. So whenever you get another thing about it, you can decide between these two cases, okay? And decide what to do. So you end up with soft delete, although you never needed soft delete for your business case. And you know, we started with simple CRUD. You remember, just expose on HTTP what you have in your database. It's very simple. Now it's not so simple because you can't just do simple delete we all like. That's worse. It's worse. Imagine you get a delete message for something you don't have in your database. And now what? I don't have it. It should be deleted. I should ignore it, right? It's not there. Someone wants it not to be there. I'm not sure why he thought that I have it, but I don't have it. He doesn't want me to have it, so let's ignore it, right? Good idea or not? Why? Yes, that's exactly this case. Someone created something and then thought that, oh no, it's all wrong, and deleted it. And we received it in incorrect order. If we ignore the delete message, we will in a moment receive the create message. And well, we won't know that there was a delete before. So we will create this thing and we won't ever delete it, okay? So the thing is, to avoid this, when we receive a delete message for something we've never seen, we actually have to create this record in our DB with the version number marked as deleted. And that becomes tricky because when you get a delete message, you don't have all attributes required to create this record. So you need to tweak your database schema to allow to create this strange thing, this ghost, okay? It's like, of course it's feasible, but we started with a simple CRUD, very basic thing, and we end up with something which is way away from being simple, especially to manage. And one last thing, HTTP patch. You know HTTP patch? What's the difference between patch and put? Okay, everyone's speaking at once, so probably everyone knows. So I will repeat it. Patch allows you to change just one attribute of the resource, okay? So now imagine that we allow to patch over asynchronous communication, and you get a change to first name with a version number, and then you get change to last name with smaller version number. You should ignore the second message because it has incorrect version number, right? But it changes different attribute. They were sent in the other order. If they arrived in correct order, you would first apply change to last name, then apply change to first name, and it would all be okay. They arrived in incorrect order, so what? If you just ignore the late message, you will end up with incorrect last name. But you also can't just ignore the version numbers and apply everything, because you can get two messages changing first name, both of them changing first name, and you must apply them in correct order to end up in correct state. I don't have a decent idea to implement patch over this. If someone has, please tell me. Aside from just versioning every attribute that we have, which seems like overly complicated, at least. So don't ever try to do CRUD over this kind of interface. When you look at HTTP and MQ, MQ can give you a lot, but it's not just a matter of changing way of transport of your API from one to another. When you switch from synchronous HTTP to anything asynchronous, you end up in something completely different. You end up in a situation where your database, designed according to business requirements, have to host things that are not even close to business requirements, like outbox, like versions, like deleted things that shouldn't be there, and you have to take care not to show them to anyone. Okay, like changes in your schema and consistency checks on your tables and things like that. Like strange questions to your product owners. How long should I keep these messages about incoming changes in bookings, because I'm not sure? Why should you keep these messages? Explain this to me. Okay, try to explain it to your non-technical product owner why you need to keep all these messages. And he won't be able to take the correct decision. He's not supposed to. And you don't feel confident enough to understand all the details. So it's a lot of knowledge that we both have to obtain, technical people and not technical people, to be able to do it well. By the way, if you ever end up in a situation where you have to synchronize things, like in the last example, it's just two streams needed to do it well. One stream does upserts, so you send a current state, and either you have this, and then you do update, and if you don't have it, you do insert to your DB, and the other case is sends delete, and you delete what's there, and that's all you need, okay? You don't need CRUD for that thing. You also will end up with procedures of restoring consistency. We had these two streams. Maybe you will have a batch processes run periodically or run manually at some point when PagerDuty wakes you up, but you will have to somehow be able to synchronize these things whenever you decide that your asynchronous real-time communication for some reason caused a discrepancy between two data stores. So the question, the thing is, asynchronous and message-driven communication is a great thing. It's a great tool for the right job. It can save you. It can provide really a lot of features like independency between teams and between data stores and things like that, and scalability and so on. But it also comes at a considerable cost. So whenever you want to apply it in your project, first thing, if you really need all this mess, and maybe it's time to get back again to your old well-known things. Your LinkedIn profile is not so important maybe for all this mess, for all this PagerDuty on Sunday and things like that. But if you really need this, it's a lot of fun. So yeah, do it. Thank you.
Thank you. Unfortunately, we have little time to the next talk, so maybe just enough for this, for the most popular question.
Sure.
What is the performance of Kafka? Any numbers?
Sorry, I don't remember at the moment. I didn't expect this question because this information is pretty easily accessible anywhere with benchmarks. Even for RabbitMQ, it was easy to find on their own blog. So sorry, I can't answer it at the moment. But if you want to reach me after the call, I will Google it quickly.
Yeah, please find our speaker after the talk. Thank you.
Thank you very much.